Hello student, I am Dr. S.L. Munde, Assistant Professor Department of Mathematics, Sri RIT College of Science, Akola. Dear student, in previous lecture we have seen half-range Fourier cosine series theoretical part. Also we have seen uh, formulas on half-range Fourier cosine series, and then we have seen one problem on a half-range Fourier cosine series formula. Okay, so in this lecture we will see another problems on a half-range Fourier cosine series. So let us turn our second problem of this topic. Before going to start second problem, I would like to tell you again symbol formulas of the Fourier cosine series. Okay, so if the function is a even type, then half-range Fourier cosine series formula is given as, let us, f of x equal to a0 plus summation n equal to 1 to infinity a n cos n pi x upon capital N. So we will use this formula to solve the problems. Okay. So where a0 is 1 upon capital L integral 0 to capital L f of x dx. So this is the second formula. Now we will use third formula for the an. An is 2 upon capital L integral 0 to capital L f of x cos n pi x dx divided by capital L. So this is the third formula. Okay. So these three formulas already we have studied in previous lecture. Okay. So generally we will use this formula to solve the half-range Fourier cosine series for problems. Okay. Now we will see the second problem on this topic. What is the question? Express the following function. This is the function in terms of the Fourier cosine series. Or there may be the question in another form. Obtain a Fourier cosine series for the function f of x equal to kx, where x lies between 0 to L by 2, and next k into L minus x, where x lies between L by 2 to L. Okay. Also we have to show that, also we have to deduce the series 1 upon 1 square plus 1 upon 3 square plus 1 upon 5 square and so on. Okay, so this is the problems. Now we will solve this problem by using half-range Fourier cosine series formula. Okay, so if you observe here, the length of the interval is given as minus L2 plus L, that is minus L is 0 and plus L is 1. Plus L is minus L. Okay, so therefore we can see that here capital L is small l. Okay, and the given function is given as f of x equal to kx and k L minus x under these conditions. Okay, then the Fourier series is given by, for the cosine series, f of x equal to a0 plus summation n equal to 1 to infinity f of x cos n pi x upon capital L. Okay, so now we will put here what is capital L, that is small l. So a0 plus summation n equal to 1 to infinity f of x cos n pi x upon small l. Let us consider equation number a1. So here we have to find out a0, then a0 and this term. Okay, so here we have to find out a0. Okay, so here a0 is a0 and an, a0 and an. So here a0 is, so this is not a correct formula. Here is a one term, that is an, f of x equal to an. Okay, so that is an into cos n pi x. Okay, this is not, this is correct formula. Okay, now here we have to find out a0, and a0 is given as 1 upon capital L. Here capital L is small l, 0 to small l f of x dx. Okay, so here capital L is a small l. So 1 upon L integral 0 to, okay, now we will split this integral into two parts. Okay, first is 0 to L by 2 and second is L by 2 to L. Okay, so 0 to L by 2, the value of f of x is a kx. So write down the kx. Then plus second integral L by 2 to L, and the value of k of x is, that is, k into bracket L minus x dx. Okay. Now we will solve this integral. Okay. So equal to 1 upon capital L, the value of this integral, the integral of this term is, that is, x square by 2, k is a constant. So this can be written as k x square by 2, and limit should be the 0 to L by 2, plus second integral plus 1 upon L, multiply 1 upon L, and multiply this k to this term. So the first integral will be kl into dx, that is kl x minus kl x square by 2. This is the second integral. Okay, and the limit should be the L by 2 to L. Okay, so if you put upper limit minus lower limit, after putting upper limit minus lower limit in this two term and solving, we will get the final result of a0 is kl upon 4, kl upon 4, and which is the a0, which is the term of a0. So let us consider equation number 2. Okay, so let us consider equation number 2, and this is equation number 1. Okay, now we will find the second term, that is an, and an is given as 2 upon capital L integral 0 to capital L f of x cos n pi x upon capital L dx. Okay, so here capital L is a small l, so therefore put capital L equal to small l, 2 upon small l integral 0 to L f of x cos n pi x upon L dx. Okay, now we will split this integral into two parts, that is 0 to L by 2 and second is L by 2 to L, and putting the values of f of x from this given. Okay, so for the first interval, the value of k of x is value of f of x is kx. So equal to 1 upon L integral 0 to L by 2, put the values of f of x, that is kx cos n pi x upon L dx, plus second integral integral L by 2 to L, and put the value of f of x, that is k into L minus x, okay, cos n pi x upon L dx. Now we will take, here k is a constant, take outside of the integral, so this can be written as, so this k is a constant, so take outside of the bracket. Okay, and here we will apply the formula, product rule formula. Okay, first function integration of second function minus, okay, minus by using the integration by part formula. Okay, so solving u into v formula, or we can say that Kronecker integration method formula. Okay, so we will split this term by using Kronecker formula. Okay, so we will get this term, first function integration of second function minus derivative of first function into integration of second function. Okay, you can use u into v formula. So plus twice kl multiply this term 1 by l to this term. Okay, so twice k upon l. So again here we will use formula u into v formula, first function into integration of second function minus derivative of first function into integration of second function. Okay, and limit should be the L by 2 to L. Okay, so here we will put the upper limit minus lower limit. So instead of x, we will put the upper limit minus lower limit. So putting upper limit minus lower limit in the first bracket, we will get these steps, we will get this step. Okay, similarly we will put upper limit minus lower limit instead of x. Okay, so we will get these steps. Okay, so if you put up carefully, instead of x upper limit minus lower limit, you can easily find out this term. Okay, so if you observe sin n pi by 2, this will become 0 and this will become 0. Okay, or we can say that this term and this term will get cancelled. If you see 2k to kk 2k upon n pi L by 2 sin n pi and minus this 2k n pi upon L by 2 term. So this both term will get cancelled, plus minus term will get cancelled. So what is the remaining term? That is 2kl upon n square pi square cos n pi, this term n pi by 2, and if you multiply to this term, so this will get, that is minus minus plus 2kl upon n square pi square cos n pi by 2. Okay, so this two times and this two times, so can be adding, we will get 4kl upon n square pi square cos n pi by 2. Okay, so adding this term and this term, we will get 4kl upon n square pi square cos n pi by 2. Okay, next term is, now we will multiply this term, so you will get minus 2kl upon n square pi square. Okay, minus into minus 1, and this term, that is minus 2kl upon n square pi square cos n pi, and we know that cos n pi, that is minus 1 to the power n, minus 1 to the power n. Okay, so we will add this term minus 2kl n pi and this term 2kl n pi. So taking common 2kl upon n square pi square, we will get 1 plus minus 1 to the power n, that is cos n pi, means that is minus 1 to the power n. Okay, so in this way we can find out the values of an, Okay, so this is the final value of the an. So from this we can find out the value of a1, a2, a3 and so on term. Okay, so here if you observe, if n is odd function, if n is odd, then a1, a3, a5, a7, a9, so these types of term will become 0. Okay, and if n is even, then we will get the some values. Okay, so for n equal to 2, put n equal to 2 in this equation, we will get 4kl upon 2 square pi square cos 2 to get cancelled, that is cos pi, minus put n equal to 2, so you will get minus 1 square, that is plus 1, so plus 1 plus 1, that is 2, so this 2 and this 2, 4kl upon 2 square pi square, and we know that cos pi, that is 1, so putting the values cos pi, that is 1, 4 minus 4kl upon 2 square minus pi square minus 4kl upon 2 square pi square. So adding these two term, we will get minus 8kl upon 2 square pi square. This is the value of a2. Now put n equal to 4 in this equation, so we will get 4kl upon 4 square pi square cos 4 pi upon 2, 4 pi means that is 2 pi, so you will get 2 pi, minus 4kl upon n square pi square minus 1 to the power 1 minus 1 to the power 4, that is plus 1. So this will becomes 4kl upon 4 pi, 4 square pi square. Okay, so 2 pi means that is 1. Okay, so putting these values, we will get 0. Cos 2 pi means that is 1. So here we will get a 0. Okay, so here cos pi means that is minus 1. So here plus 1. So this term and this term cancelling, we will get 0. Similarly, we can find out a6, that is 4kl upon 6 square pi square cos 6 pi upon 2, that is 3 pi, minus 4kl upon 6 square pi square, and this is, that is 1. So calculating this term cos 3 pi means that is minus 1, so this will become minus 8kl upon 6 square pi square. Similarly, we can find out a8. Okay, so a8 is 4kl upon pi square 8 square cos 4 pi, and cos 4 pi, that is 1. So this term and this term will get cancelled, that is a8 will get 0. In this way we can find out the a1, a2, a3, a4 and so on term. Okay, now we will put these values in original equation number 1, in this equation number. Okay, first of all we will expand this for n equal to 1, 2, 3, 4 and so on. Okay, then we will put the values a1, a2, a3, a4 and a6, a8 and so on term. Okay, so after putting and solving, we will get a0, that is kl upon 4 minus 8k upon pi square will be the common term. Okay, from this remaining term. Okay, So in bracket there will be the 1 upon 2 square cos 2 pi x upon L plus 1 upon 6 square cos 6 pi x upon L plus 1 upon 10 square cos 10 pi x upon L plus and so on. Okay. So this is the required Fourier series for the given function f of x. Okay. Now if you observe, this function f of x satisfies the Dirichlet conditions. Okay. Since x equal to 0 is a point of discontinuity and this series converges to f of 0. Okay. So therefore by using the formula 1 upon 2 x0 plus f of x0 minus. Okay. So we have already learned in second or third lecture. Okay. So at x0 equal to 0, so we will get 1 upon 2 f of 0 plus 0 plus f of 0 minus 0, that is f of 0. Okay. Now at x0 equal to 0, what is the value of f of 0? So at x0 equal to 0, so f of x0, that is 0 plus 0 equal to kx. So this is the value of kx at x equal to 0. So this will get the 0. And f of 0 minus 0 at a value of x equal to L. So you will get you will get 0. Okay. So this is the f of and which implies f of 0 equal to 0. So you will get f of 0 equal to 0. Put f of x equal to 0 at x equal to 0 in this equation. At x equal to 0, put x equal to 0 in this equation. We will get left hand side is 0. F of 0 is 0. And right hand side is kl upon 4 minus 8 kl upon pi square. 1 upon 2 square and cos 2 pi x is 0. So cos 0 means that is 1. So this cos 0 cos 0. So this will becomes 1 1 1. Okay. So what is the remaining term? 1 upon 2 square plus 1 upon 6 square plus 1 upon 10 square plus and so on. Okay. Now in next steps we will transfer this term to RHS side. Okay. And take cross multiplication. Okay. So after solving, so you will get 1 upon 1 square plus 1 upon 3 square plus 1 upon 5 square plus and so on equal to pi square upon 8. Okay. So this is the value of the given term. Okay. So which is the required solution of the given term. So this is the complete solution of the problem. Now we will see third problem on a Fourier cosine series. The problem is given as obtain the Fourier cosine series for the function f of x equal to x square where x lies between 0 to 2. Okay. So we will solve this problem. So what is the given? The Fourier series for this function is given as f of x equal to x square. X square is given a0 plus summation n equal to 1 to infinity a n cos n pi x upon 2. Okay. So if you observe this function is already even function. If put x equal to minus x, so you will get x square term. So this function is even type function. So therefore a0 is 1 upon 2 0 to L, that is 0 to 2 x square dx. The integral of this term, that is x cube by 3. So putting upper minus lower limit, you will get 4 by 3. Then we will find out second term, that is a n coefficient 2 upon capital L. L means 2. 0 to 2 x square cos n pi x upon 2 dx. Okay. Now we will use here formula u into v formula. First function into integration of second function minus derivative of first function into integration derivative of first function into integration of second function. Or you can use here Kronecker integration formula. Okay. So we will put upper limit minus lower limit. So after putting upper limit minus lower limit, okay. So sin 0, this term will 0, this term will become 0. Okay. So only cos n pi x term will exist. Okay. So upper limit, put upper limit. So you will get upper limit and minus lower limit, only this term will exist. Okay. So after putting upper limit minus lower limit, you will get 8 upon n square pi square 2 cos n pi. And when that cos n pi, that is minus 1 to the power n. Okay. So 2 into 8, that is 16, minus 1 to the power n square upon pi square. Okay, so this is the value of an. Now put the values of an and a0 in this equation. Then equation a2 will becomes f of x, that is x square 4 by 3, that is a0, plus 16 upon pi square. If you expand this term, so you will get a1 cos uh, n pi x 1 pi x upon 2, a2 cos pi x n pi x. Okay, so in this way you will get the term. Okay, and this is the required Fourier series of the given function f of x equal to x square. Okay, so this is the third function. Now I will give you some homework problem for the practice. So this is example number 1. So this is a Fourier sine series and cosine series. You have to solve this problem by both series. You can solve this problem by only Fourier sine series, and this is related to Fourier cosine series. Okay, so you have to solve this problem as a for the homework purpose. Okay, so dear student, here we have completed all the points of the Fourier series unit. Okay, so with this lecture we have completed unit number 3rd, that is Fourier series. In next lecture we will start unit number 1 of this paper. Okay, so in next lecture we will start unit number 1.